So in this video, we're going to go over evaluating limits algebraically. So first thing is, not all limits can be found using direct substitution. Now, we kind of hit upon this already when we went over it in estimating limits graphically because of the fact that not all functions are continuous. So if a function is not continuous, you have to check to see whether or not that point of discontinuity is occurring at the value you're trying to take the limit of. So the reason you can't always use direct substitution is because not all functions are continuous. So let's go over two examples. So if I have the limit of the function x plus 5 as x approaches -2, and the limit of x squared plus 5x plus 6 over x plus 2 as x approaches -2. And so let's look at the first one, okay? So for the first one, x plus 5 is the function you're taking the limit of. And x plus 5 is linear. We know what this thing is going to look like. Okay? And it's continuous. You have to know what you're working with. I'm working with a linear function. I know it's continuous throughout the entire function. There are no domain restrictions for x plus 5. Okay? Nothing funny is happening here. So I know that the limit as x approaches -2 of x plus 5 is just going to be what is happening when x is -2. Okay? And that is going to be, notice I just did direct substitution. Okay? That's going to be 3. So the limit of x plus 5 as x approaches -2 is 3. Because I know it's continuous when x is -2. So that's why I'm going to be using direct substitution here. Now, direct substitution here, well, I notice I have a rational function here, right? And let's see, if I factor this becomes x plus 3 over times x plus 2 over x plus 2. Do I have domain restrictions in number 2? Absolutely. This is a rational function. X cannot be -2. So I know that number 2, this function here, is discontinuous. So I have to be careful here. Is it discontinuous when x is -2? Absolutely. What is it, though? Because if it's a rational function, it could be a whole or it could be a vertical asymptote. For number 2, right, we have a whole when x equals -2. So what I can do here, okay, notice if I try to use direct substitution here, okay, I get 0 squared plus 5 times 0 plus 6. Oh, I'm sorry, not 0. Let me erase that. Direct substitution, I get -2 squared plus 5 times -2 plus 6 all over -2 plus 2. That gives me 4 minus 10 plus 6 over -4, -2 plus 2, not -4. So we keep going. 4 minus 10 plus 6, that's 0. -2 plus 2, that's 0. 0 over 0 is what's called an indeterminate form. There are 7 total indeterminate forms. However, we're just going to hit this one, 0 over 0. Now, if you get the indeterminate form of 0 over 0, okay, you need to look to try and rewrite the function, not change its value, okay, not change value, to try and evaluate algebraically. So what we can do with this one, okay, notice, what do we have here? We have a whole. if I eliminate the common factor, right now I have x plus 3 times x plus 2 over x plus 2. If I eliminate the common factor, I have x plus 3, okay? If you think about what this graph looks like, okay? It's just got a hole. It's the line x plus 3, but it's got a hole when x is negative 2. Right? There's a hole right there. But does your limit exist at x equals negative 2? Yes. If you just have a hole there, right? Nothing else is happening. You know that you exist. This limit exists. You don't exist at negative 2, but the limit as x approaches negative 2 exists. And if you look, okay, so we crossed out the x plus 2. And so what we've really got the function of here is x plus 3. If we plug this in, direct substitution, we can now use, because we no longer have the indeterminate form of 0 over 0, we get 1, which is the y value of the hole of the point of discontinuity. So if you have the indeterminate form of 0 over 0, it does not mean that you can't evaluate the limit, and 0 over 0 is not the limit. It means you have to try and rewrite your expression so that you can take the limit algebraically. Now, let me give you another example. Number 3, let's say the limit 1 over x minus 3 as x approaches 3. Okay, we know we have some discontinuity here, and we know that the discontinuity is happening when x equals 3, and that's the value we're trying to find the limit of. So, I shouldn't say of, as x approaches 3. So, if we were to look at this graph, we know that we don't have a hole happening. What we have happening is a vertical asymptote, right? We know that it's happening when x is 3. And we know this graph is going to look like this. Now, if you were to try direct substitution right now, you would get, okay, just know what you have. I know I have a rational function, vertical asymptote x equals 3. I tried direct substitution, and I get 1 over 0. Now, this isn't called indeterminate form. This is called infinite form, okay? When you get a number over 0, it's called infinite form. And what you have to do is, you're going to have to get away from algebraically for a second, and you're going to either have to look at the graph or estimate it numerically. So if you look, okay, I got the infinite form. So what I have to do is I have to look, okay, the left-hand side of, this is the line x equals 3. The left-handed limit is going to negative infinity. The right-handed limit of x equals, as x approaches 3, is going to positive infinity. Therefore, the limit does not exist here. So, when you have the infinite form, okay, you're not going to try and rewrite it. It's either going to be infinity, negative infinity, or this limit does not exist. So, if you want another example, let me go over that. You can have a vertical asymptote and it still exists. So let's say we want the limit as x approaches 0 of 1 over x squared, okay? 1 over 0 squared, okay, that's going to give us 1 over 0. That's going to give us that infinite form. If we were to look at the graph here, okay, 1 over x squared looks like this. So, left-handed limit is going to infinity. Right-hand limit, as x approaches 0, is going to positive infinity. So, the limit would be positive infinity here. Okay, so you have to do a little bit of algebra by, you're trying direct substitution, you're getting the infinite form, so you got to go to an alternate way of doing it. But let's stick with the ones that we can figure out algebraically. So, what we need to remember about the indeterminate form, okay, and the only one we're hitting here is 0 over 0. Okay, there are still 6 more. Okay, that's 0 over 0, not the division symbol. Okay, we are going to try and rewrite the function, not change its value, to evaluate algebraically. Okay, that's what we have to try and do. So, Let's get to many examples. Evaluate each limit algebraically. Number 1, our function will be x minus 1 over x plus 7, and we're going to take the limit as x approaches 2. So think about what you have here. You have a rational function, okay? Are you going to have, is this continuous? No. Where is this thing discontinuous at? This thing is discontinuous when x equals negative 7. So, is it discontinuous when x is 2? No. Nothing funky is going to happen when x is 2. So, we can just plug 2 in. So, what's going to be the limit as x approaches 2 of x minus 1 over x plus 7? 1/9. If you want to check, okay, you can graph, okay, if you want to check to see if you did this right, graph x minus 1 over x plus 7, okay, graph that, and check when x is 2, what is y? And it's going to be 1/9. Number 2, the limit of x squared minus 9 over x minus 3 as x approaches 3. Okay, another rational function. So, is domain all real numbers here? No, it's not. Okay, we know that we have some points of discontinuity here. Even if it was all real numbers, okay, that doesn't necessarily mean that you can find the limit, that it's not going to be indeterminate form or there's nothing funky happening, okay? But we check, this is a rational function, okay? We know what's happening here. And we know that this has points of discontinuity. We know that it's going to be the point of discontinuity. Something funky is happening when x equals 3. But we have to check, is this a whole or is this a vertical asymptote? So let's factor and see what we get. So this is really x plus 3, x minus 3, over x minus 3. So this thing is a whole. So that's good because what we know about wholes are that the limit exists at the value of the whole. So the way we know that this is actually, before we even cross it out, okay, what we check for is we plug it in. 3 squared minus 9 over 3 minus 3. 9 minus 9 over 3 minus 3. 0 over 0. As long as you know that nothing funky is happening, you can try and plug in that value, 2 minus 1 over 2 plus 7. Now, what I mean by funky is if this was a piecewise and you could have those little breaks in the graph where you then have this down here, okay, you want to make sure nothing funky is happening in your graph and nothing like that's occurring here, okay? So everything is good that we've got going on here, okay? So 0 over 0, indeterminate form. So we look, okay, I can factor x minus 3 over x minus 3. I get x plus 3. What's the limit? As x approaches 3 of x plus 3, I'm now going to be able to do this because I was able to rewrite this expression in some way, and now I get 6. Okay, next example. Let's say I do the limit as x approaches 1 of 1 over x minus 1. Okay, rational function. If I plug 1 in, I get 1 over 1 minus 1. That's 1 over 0. This is that infinite form. Okay, so I've got something funky happening when x equals 1. What is it this time? This time it's a vertical asymptote. So we talked about what we would have to do here. Okay, we would want to look at the graph. And the graph is going to look something like this. And so, does the limit exist as x approaches 1? No, the limit does not exist here. Notice we had to get a little bit off of algebraically because we noticed that this was the infinite form. Okay, number 4. Let's do the limit as x approaches 2 of the square root of x plus 7. So the square root of x plus 7. Let's plug in 2. What do we have here? The square root of 2 plus 7. It's the square root of 9. That's 3. Is there anything funky happening when x is approaching 2? No, this is just a square root function, right? So we know that the limit is going to be 3. Number 5, let's do the limit as x approaches 4 of x minus 4 over the square root of x minus 2. So let's see. Okay, looks like we're going to have this is going to be discontinuous in some areas because we know that the denominator can't be 0. Okay, but let's see. We plug in 4 and we get 4 minus 4 over the square root of 4 minus 2. That's going to be 0 over 2 minus 2. That's going to be 0 over 0. Oh, so we've got the indeterminate form. Okay, so that means let's try and see if we can write this a different way. Well, one thing we can do, if we have a radical expression, we see that it's in the denominator, let's try and get it out of the denominator. So to get it out of the denominator, we would need to multiply by the conjugate of the denominator, which the conjugate of the square root of x minus 2 would be the square root of x plus 2. And so if I multiply this out, I've got 2 terms by 2 terms, so I'm going to get 4 terms. X times the square root of x is just x square root x. X times 2 is 2x. Negative 4 times the square root of x is negative 4 square root x. Negative 4 times 2 is negative 8. Denominator, square root of x times the square root of x. That's giving us the square root of x squared, which is just x. That gives us plus 2 square root x. That gives us minus 2 square root x. Negative 2 times 2, that gives us negative 4. Those cancel. And if I just clean this up a little bit, notice these terms have a common factor. The common factor is the square root of x. So I'm just going to put them next to each other. X square root x minus 4 square root x plus 2x minus 8 over x minus 4. Now remember, you got the indeterminate form. So what you're looking for is there a way to simplify this expression by rewriting it so that x minus 4 cancels out? So there must be something else we could do, because right now, we would still get 0 over 0 if we plug in 4. So what you have to try and do here is factor the numerator. You want to factor this numerator and see if you can get a common factor of x minus 4. So these two terms have a common factor. So 4 terms you factor by grouping. So this is x square root x minus 4 square root x plus 2x minus 8. The common factor, the greatest common factor between these two terms is the square root of x. You take it out, you get x minus 4. Greatest common factor here is plus 2. You get x minus 4 all over x minus 4, right? Now you're not done. I didn't really need to write that over x minus 4 yet because you haven't done the complete factoring by grouping yet, right? So now you take out the x minus 4 and the other factor is the square root of x plus 2, okay? All over x minus 4, okay? So this is what this right here is the same as this. So we can see that we're actually having a whole because x minus 4 cancels out, and what we really have, okay, is just, it's a point of discontinuity. When x equals 4, it's a whole, and we just have the radical function, the square root of x plus 2. So now, direct substitution again, the limit of x minus 4 over the square root of x minus 2 as x approaches 4 will be 4. So yes, there is a whole at 4, but the limit exists as x approaches 4. So let's do another. That was number 4. So number 5, let us do the limit of x squared minus x minus 2 over x to the third minus x as x approaches, -1. So we're going to want to plug -1 in. Notice this is a rational function. So let's see, -1 squared minus -1 minus 2 all over -1 to the third minus -1. So that's going to give us 1 plus 1 minus 2 over -1 plus 1. That's going to give us 0 over 0. So we've got that indeterminate form again, which means we have to try and rewrite this expression. We know that this thing is not continuous over the entire function, so we have to be careful here, see what's going on. So what would you try and do here? Factor, okay? X squared minus x minus 2. That's going to be x minus 2 times x plus 1. X to the third minus x. I could take out a greatest common factor of x. That leaves me with x squared minus 1. So that's going to factor further. And difference of 2 squares. And so that's what we get. All right. Notice we can cancel out x plus 1 over x plus 1. That is the whole. The whole is at x equals -1. That means I'm going to be able to simplify this. And am I going to be able to plug -1 in now? Yes. That's going to give me the limit as x approaches -1 of x minus 2 over x times x minus 1, okay, with a whole at -1, gives me -3 over -1 times -2. So that's going to be -3 over 2. So that's going to be the limit there. So let's do another. Number 6, the limit as x approaches 5 of 10. So you're saying the function is the y value of 10. So no matter what x is, the output is 10. So what is the limit as x approaches 5 of the function 10? That's going to be 10. All right. Let's do 2 more. Actually, we'll do 3 more. So let's do the limit as x approaches 0 of the square root of x plus 64 minus 8 all over x. So we got some funky things happening here, we could tell. Okay, we have variables in the denominator. Let's plug in 0 and see what happens. We got 0 plus 64, the square root, minus 8 over 0. So this is going to be the square root of 64 minus 8 over 0. This is going to be 8 minus 8 over 0. This is going to be 0 over 0. So we've got the indeterminate form again. So we're going to try and rewrite this. Now, in one of the previous problems, okay, we had, let's see, where is it? Let's see, let's go back here. We rationalized the denominator to see if it gave us anything. And it did. Now, perhaps what's going on here is we've got this 0. If we put in the denominator, it's going to give us 0. So perhaps that this was the rational expression for a previous expression in which the radical was in the denominator. And if the radical was in the denominator, perhaps we would not be getting 0 in the denominator. So sometimes you might need to, if you have a radical expression, you might need to rationalize the numerator. So we need to actually try and see if rationalizing the numerator helps us. So if I want to rationalize the numerator, that means we're going to actually end up with the radical sitting in the denominator, which is perfectly fine. So the square root of x plus 64 plus 8 is going to be what rationalizes the numerator. So the square root of x plus 64 times the square root of x plus 64, that's just going to give us x plus 64 plus 8 square root of x plus 64 minus 8 square root of x plus 64, and then negative 8 times 8 minus 64 all over x times x plus 64 plus 8x. Okay, so now let's see what we got going on here. All right, that cancels with that. This cancels with this. Let's clean this up a little bit. We've got x over x square root of x plus 64 plus 8x. Now you could see if I try plugging 0 in still, I'm going to end up with 0 over 0. So you have to just keep going. So let's see. I've got two terms, 1, 2. I've got a common factor of x. So that's going to be x over x times the square root of x plus 64 plus 8. So let me move that out a little bit. Sorry. So I've got a common factor of x, which is good because what makes x 0? 0, 0. So we've actually got a hole at that 0. That's what you're hoping happens, that cancels out. The factor cancels out. Okay, notice at number 5, we needed x plus 1 to cancel out. Here, we need x to cancel out. That's 1 over the square root of x plus 64 plus 8. So now we can try and plug in 0, 1 over the square root of 0 plus 64 plus 8. That's 1 over the square root of 64 is 8. 8 plus 8, 1/16. So we just have a hole when x is 0 in this function. Okay, let's do the next one we will do. Number 8 will be the limit as x approaches 0 of 2 over the square root of 3x plus 4 minus 2. Well, actually, we want to make this x over the square root of 3x plus 4 minus 2. So try that one on your own and pause the video. And when you're done, play the video and see if you got it right. So first, make sure you change that to x over, it wasn't 2 over, it was x over the square root of 3x plus 4 minus 2. So if I try and plug in 0 now, I'm going to get 0 over the square root of 3 times 0 plus 4 minus 2. I'm going to get 0 over 0. So indeterminate form, I got to try and rewrite this thing. I'm going to try and take the radical and put it in the numerator. So I'm going to rationalize the denominator this time. And if I do that, I got to multiply by the square root of 3x plus 4 plus 2 over the square root of 3x plus 4 plus 2. That's going to give me x square root 3x plus 4 plus 2x all over. This times this gives us 3x plus 4. This times this and this times this cancel each other out. Negative 2 times 2, negative 4. So let's see what we got. 4 minus 4, they cancel. So we've got x square root of 3x plus 4 plus 2x all over 3x as x approaches 0. So I'm hoping a factor of x cancels here. I see I've got 3x in the denominator, so I do have a factor of x here. I'm trying to see if I have a factor of x here, and there's two terms, and I can take out an x. So it does cancel, and it leaves me with the square root of 3x plus 4 plus 2 over 3. So can I plug 0 into this? Yes. 3 times 0 plus 4 plus 2 over 3. That's going to be the square root of 4 plus 2 over 3. That's going to be 2 plus 2 over 3. That's going to be 4/3. So we can have a limit here. Okay, and we're going to do one more problem. Number 9. And number 9 is going to be the limit as x approaches 6 of the quantity x minus 2 squared minus 16 over x minus 6. So we got a rational function happening here. we can see we have some point of discontinuity, but let's see what happens when we plug 6 in. So we get 4 squared is 16. This is 16 minus 16 over 0. This is 0 over 0. We got the indeterminate form again, so we're going to try and rewrite this. Now, one thing that's sticking out when I see this is the fact that I have a binomial squared sitting in the numerator. So what I would do in this type of situation is, okay, I'm not going to try and factor anything right now. What I'm going to do is the opposite of factoring. I'm going to undo x minus 2 squared. So that's going to give me x minus 2 squared is x squared minus 2x plus 4. So my numerator is x squared minus 2x plus 4 minus 16 over x minus 6. And let's see what that cleans up to. So that's going to be x squared minus 4x minus 12 over x minus 6. Okay, so the numerator is in standard form, x squared minus 4x minus 12. So we're really taking the limit as x approaches 6 of x squared minus 4x minus 12 over x minus 6. Okay, we're still going to get 0 over 0. And so let's see if there's anything we can now do with this expression. So now what would you try and do here? You would try and factor. So that's going to be x minus 6 times x plus 2 over x minus 6. So notice, we are trying to find the limit as x approaches 6. So we're hoping that x minus 6 is a factor, a common factor that cancels. It happens. So that means we just have a whole at 6. And so we're really just going to take the limit of x plus 2, and that's going to be 6 plus 2 is going to give us 8. So when you get the indeterminate form, okay, you need to try and rewrite the expression to see if you can find a limit algebraically. So if you are taking the limit of f of x as x approaches a, and you get the indeterminate form 0, 0, you want to try rewriting the expression in some way in hopes that the factor x minus a cancels out.